What I'm going to talk about is software design, and in the earlier years we used to talk about software design in a much more general way, and then we realized, this is after all for extreme scale computing, which means that you are all going to be presumably working with heterogeneous platforms. And so today's presentation is more geared towards how would you design software for a heterogeneous platform. In the previous years, if you want to see more details on the general software design principles that we talked about before, you can go and look at one of the earlier from the earlier years, and that is much more general. Okay, the license slide, etc. So I will also put this disclaimer out there right up front, is that most of what I've learned about software and most of the inferences I've drawn about a good software design practice have come from learning on the job and hard experience of basically being the software architect for a multi-physics, multi-community, multi-component, etc. code, and that is Flash. So quite a bit of what you're going to hear about is derived from that, but I have been assured by people who have listened to my presentations on this issue, who have written other similar codes, that these are pretty general things that they did too. Okay, so there is certain things about scientific software that require approaches to design that are pretty unique to the kind of complex software that we write in scientific world. One is that, as David mentioned before, there are many multidisciplinary teams, and what that means is that there are many facets of knowledge that are involved in building the code, and for anyone to know everything is simply not possible, right? What that means is, its design implication is that you have to think about separation of concerns right from the beginning, where things like the infrastructure is somebody's responsibility, specific physics solvers, physics, chemistry, biology. I'm just going to be using physics to imply all of them because that's how I'm used to speaking, but that's not excluding the other domains, right? But so those are somebody. So people who have expertise in that can focus on that. People who have expertise in numerical methods can develop algorithms and not have to worry about the other aspects of the code. So basically what this principle of separation of concerns in your design does is it shields developer from knowing complexities that are not, that should not be necessary for them to know. Then there is this thing that, typically in these tutorials we also used to talk about things like agile and software development cycles. We are not doing that today because there is a lot of, again, material out there that you can read about and learn. But one of the developments in the last last couple of decades has been that people turn their noses up at everything other than agile methodology for software development. And I am going to come out and say that that's not entirely true. Because in your scientific code, there are two distinct components that need different treatment. Whether you like it or not, your code, if you are doing any kind of multiphysics, is going to have a backbone, an infrastructure that provides things like discretization method, the I/O operation, the whole bookkeeping of running your code, whether it is for simulation or for analysis, right? Now, this cannot change very rapidly. You have to design it in such a way that extensibility of the features that you want, the capabilities that you want in your code to be in terms of the actual solvers can be extended, because your code is going to be used in ways you didn't think of before. And so when you are designing your infrastructure, you have to follow what has traditionally been called a waterfall model, in the sense that you do take a longer time to do your requirements gathering, and you give a lot more thought to what your interfaces are going to look like and the capabilities you're going to bring into it. The science models, the numerical methods themselves, are likely to be having ongoing research associated with them, which means that they're going to be changing rapidly, and that's where you want a rapid cycle of development and therefore the agile methodology. So in addition to the difference between long changing and quick changing, there is this aspect also that the infrastructure is logically complex but mathematically simple, and typically your numerical methods are mathematically complex but logically not very complex. So that also makes a difference in how the life cycle ought to go. And the last one I already mentioned is that every time people don't, in our world, people typically don't use the code twice in the same way because they're trying to do new science, and therefore they want to use it somewhat differently from how they used it before, which means that in your code you should absolutely have a possibility of extensibility and customizability for every new time that you want to use it. So how does that translate it into a system of software development? And that is what is encapsulated here is that the top boxes are the subject of research, models, numerics, and mathematically complex. So you basically are just treating them differently to and encapsulating to plug and play. So these are your more stable, these are your infrastructure, data structure, movement, etc., etc. But even though you treat them differently and encapsulate them to plug and play, some things apply to both types of code, and that is that you should have them logically separable functional units of computation. That should be encoded into a framework. All of the code modules, irrespective of whether they belong to the infrastructure and slow changing or the fast changing, you should differentiate between private and public. That just makes the maintenance easier in future, and then you should define interfaces for both of them with the thought of how the interoperability between various modules will work. One of the things that also that many people miss in designing their code is they think about a specific programming model first. So people will say, I'm writing an MPI code, and they will go ahead and write an MPI code making use of the features that are available in MPI and sometimes shoehorning them into your code. That is not always the best approach. The best approach is to think about the principles that MPI encodes, for example. What is your best domain decomposition? Think about how you're going to work out the parallelization into your code in your design process first, and then do the binding to an actual design, an actual programming model as late as possible. This way, what you have done is you've designed your code in a way that should MPI go out from under you and something else with a slightly different interface comes along, your code will not just become useless. There will be isolated pieces of code where you can incorporate these changes and still continue to use your code. So here is an example from Flash, which is now actually FlashX, is for the extensibility in design. So what we have in code is that it is basically it is divided up into many components. Each component carries along with it its meta information about the other code pieces that it will work with, the state variables that it will need, the runtime parameters it will need, the other code components that it depends upon, etc., etc. So this intelligence about a particular component is distributed. It's not centralized, it's distributed, and it's encoded along with the component itself. Then there is a tool that then parses this information and puts together an application instance which is consistent and then can be compiled and built. So here we have an example for, let's say we are working with a code where we just have a driver which has API for the grid, which is your discretized mesh and so on, and now we want to add another unit to it which computes shock hydrodynamics. Now this is a totally synthetic example. I mean, Flash has had hydrodynamics from the day it was built, but let's say that that's what we were trying to do. So the changes that need to happen to the code in order for it to be able to add this hydrodynamics unit is this, that you just have this code, this section of the code come in. The changes that you need are to the driver in the flash, which now in addition to calling grid related functions calls hydro, and there is nothing else, and the configuration file of grid itself remains unmodified, everything here remains unmodified. This is all that happens is that flash driver becomes available of an additional unit that it just needs to call. So, from that example, the one way in which you can think about separation of concerns is that there are these two different life cycles. For the infrastructure, where you are looking at the requirements, you are doing a software and architecture and API design, implement, test, maintain, and this is the loop back for any enhancements to it. You can go ahead and do the development of your science components completely independently. The place where they need to interact with one another is when you are designing the API for your new unit in terms of how does it want to let itself be known to other components in the code should they want to call it. And the integration in terms of so it's not always true that you can just bring in a physics unit and add it. Sometimes you need more features from the infrastructure than it already had, and therefore you may need to do some augmentation. But what this is still allowing you to do is your numerics can be developed and designed and validated, say in Python or MATLAB before you need to integrate it into the code, and then you can go ahead and integrate it overall into the code and you're good to go. This model used to be perfectly valid when we were working with distributed memory model or the clusters model of calculation of developing software. And the question is, do we need to change it substantially for heterogeneous platforms? And the answer is not really. The only thing that is that things involved in the enclosed ellipses become a lot more complex and involved. And this is where the maximum change happens, and that is in terms of integration. And as I go more into the details of designing for heterogeneity, you will see why this is the case. So, keep this diagram in mind as you listen to the portions where I am talking about designing for heterogeneity. So, to take a look at the kind of heterogeneity we are talking about, we have three axes of heterogeneity that we are dealing with. One of them is computation, in the sense that your computation devices could be CPU, GPU, some other kind of accelerator, FPGA, who knows what comes in future, right? Memory is the simplest to think about is that, there we go. The memory is that in the CPU you have cache hierarchy. On the GPU you have device memory, which may or may not have any kind of cache hierarchy, which it may be completely flat. Within the node also you may have things like burst buffers and NVRAM that serve very specific purpose, or you could have some other type of memory, who knows again what's in the pipeline. For example, there is stacked memory in the pipeline and so on, and whatever, being in extreme computing, whatever hardware comes along and becomes available to you on the platforms, you will want to use it. And you will, in order to speed up your calculations, in order to be more efficient with your computations. In the network then you have again heterogeneity in terms of how would you move data within the node versus how would you move data off the node. Then also some configurations have specific nodes that are meant for I/O, and so you need to move your data to the I/O nodes, and all of these contribute to the cost of your calculation, and so you need to be aware of the cost and you need to minimize the cost and optimize your run. Within the memory access, of course, there are many different memory access models such as unified memory, GPU direct, explicit transfer, and it is never clear that for every situation any one of them is going to be the best option. It is that for one situation one is better, for another situation another is better, and so on. So we have to deal with all of this. So the mechanisms that codes will need in order to tackle these challenges, in order to work in this environment is, you need a mechanism to unify the expression of computation, because you do not want to have to write code, a separate code for CPU, a separate code for GPU, a separate code for another device, and so on, right? What you want to do is you want to express your computation once, and you want to be able to reuse it on different target platforms. And it's not just in terms of the flow of control, but it is also the difference in data structure. So you need to a way of unifying all of that. Then you need to have a mechanism that can move work and data to different computational targets. So in distributed memory, again, it was a simple thing. You did your domain decomposition, you mapped one section of the domain to one of the nodes, MPI took care of internode communication, and you were good to go. That's no longer true. Now you have devices to which you want to move data within the node. You may need to move data off the node, and so on. And then when the data and computation has been moved to the device, you want to be able to launch the computation at the target device, right? And you want to do it, if you want to utilize your resources well, you want to do it in such a way that the latency of data movement is hidden, it becomes a hidden cost, that this doesn't remain an explicit cost, because that's usually very expensive. And then that by itself doesn't complete your job, because there is this thing that how do you figure out which computation should map where? In your multi-physics, multi-component code, if you are in a situation where you can just move everything to the GPU and all of your algorithms work well on the GPU, for example, you're good to go. But in most situations, that is not going to be the case. And also, even if all of your code is good on the CPU, on the GPU, CPU is a resource on your platform. And if you're not using it, you're wasting it. So you may want to divide up work between devices, and so you need to have some way in which you can do this mapping, and so that you can encapsulate your computation so that they can move, and then so the dependencies are explicitly explained. And so what you might end up needing is a expression, a cost model that lets you make a choice, makes you choices about where you want to move your code. So what do we need in order to accommodate these mechanisms that are needed by the code? We need abstraction layers to unify the computation. We need code transformation tools to translate the dependencies, to understand and translate the dependencies into code that is executable. And we need data movement orchestrators, right? So keeping that in mind, and now I'm going to delve a little deeper into each one of these mechanisms that the code might need. So unification of computation expressions. The underlying idea is that you want to use the same algorithm. Actually, if you are lucky, your same algorithm might work well on both the devices, in which case what you need is you want to have just different data layouts and different sequence of operations. So what you need is a way for compiler to know that the expression can be either the compiler or the tool, some abstraction tool that you might be using. It's a way to let the compiler know that this expression can be specialized in many ways. And then you give the definition of your specializations. So in C++, and many of the tools that are available for such abstractions are based upon C++ for the simple reason that C++ template metaprogramming provides you with a mechanism for expressing the code with templates and specializing with the templates metaprogramming, right? But again, we are all operating in extreme computing, and we are all operating in multi-physics era, and so whether you like it or not, you're going to come across codes that are written in Fortran and C. And therefore, these abstraction options are not really options for you, may not be options for you. So the thing to do is then to think about other ways in which you can have this very same, again, here the trap that people will usually fall in is that even if you're working in C++, is that you will pick the tool you want to use. It may be, there are several of them. You will pick the tool you want, and then you will code to that tool so that you become completely tied to that tool, and that's never necessary. What you should be doing is you should be thinking about where your template, where would you put the template first, and you should design according to where you want unification and specialization happening, so that if you want to switch the tool, the places where you need to make your changes are contained, and that you don't have a hard dependency on a tool. I will give you examples from Flash where we have gone, because FlashX is a Fortran code. So, we have actually gone ahead and designed this entire tool chain for ourselves, and we believe that that is actually easily adaptable for all codes, including C++ codes, but that comes a little bit later. But in unification of expressions, there is a situation that many people have faced, and this is that your algorithms simply need to be different on different devices to use them effectively. In order to accommodate that, then your code design should be such that it can support multiple alternative implementations seamlessly. So, that is the need there. For moving work and data to the target, the first thing that you need to think about is parallelization models, because you need hierarchy and parallelism. Just the simple domain decomposition of the kind that we used to do for distributed memory is no longer valid. You have to think about different levels at which the parallelism needs to be expressed. So, the most common hierarchy right now is that you use distributed memory model for off-node communication, and you use other kinds of communications for within the node. So, most prevalent ones for off-node computation are distributed memory model and PGAS model, and even though PGAS model is a shared memory model, if you don't pay attention to the locality of your data in the way that you would for MPI, you would not get a good performance. So, effectively you still have to think about your domain decomposition in the same way, you are just encoding it with different programming models, right. For most of the C++ based abstraction models, assigning work within the node just works with parallel for, and there are many different ways in which these parallel fors are written, but they are but they make the details somewhat transparent to the user. But that, in some cases it works well, in other cases it does not work well. Many people go with the directives option, where they can be OpenACC, OpenMP, or some other kinds of directives which explicitly tell the code that this is where the data needs to move, or people can just work with unified memory, and parallel fors typically work with the unified memory mode much better. If however, and there are some other mechanisms that are available that have much more complex data movement capabilities, and those typically tend to be the asynchronous task models, tasking tools such as Legion, StarPU, Magma, HPX, and so on. What these tools do is they have to them a task is a completely encapsulated and self-contained unit of work and data that needs to be moved, that can be moved as a unit to a target, and it can be executed on that target. So, these things do a much more complex asynchronous computation. Not everyone uses it, but it is the most flexible way of thinking about configuring your application, but the caveat is that it comes with its own overheads, and the overheads are not always justified. So, for mapping work to targets, the basic idea is that you infer the structure of the code, you, based upon the structure of the code, then you infer the map between the algorithms and devices. Then you infer the data movements that need to happen in order to move the data from map that algorithm to that specific device, and then you map the computations to the devices. These can be specified, as I said before, through constructs or pragmas, but the bottom point, and it may not be an abstraction layer that is doing it, may be a user that is actually manually doing this inferencing and mapping. But the point is that your code, the performance of the code will depend entirely upon how well this mapping is done. So, now I will go through all of these mechanisms, as I said, with the example of FlashX and how we are tackling them. And the reason why I am doing it this way is because our designs, and of course it is biased because it's me, and I've been responsible for a lot of this design, and I think that this is the best. You may not think so, but so the way we are doing is mapping our tool chain exactly to these different mechanisms, and we have done a separation of concerns in our tool chain also, where each tool just targets one type of mechanism that it needs to handle, and that each individual tool is simple. All of our tools, well, the data movement orchestrator is the most complex tool, but the rest of them are fairly simple tools, just simple Python or JSON based tools that can be maintained by non-experts, and they deliver the performance portability solutions that very much more complex C++ tools are delivering. So, our mechanism to unify the expression of computation is we use macros, because that's an easy way to avoid code duplication, but macros by themselves do not suffice. So, what we have done is we have provided macros with their own inheritance mechanism, so that you can have macros be multiple alternative definitions of the same macro name, and that lets you specialize in a way very similar to the templates, right. Then there is the mechanism to move work and data to computational targets, and what we have done is we have developed a domain specific runtime. This is our most complex tool. The author is sitting right over there. This is written in C++, but conceptually even this tool is very simple. It is just an execution engine. It does not do any inferencing itself. So, what it is basically an extended finite state machine, which has a queue into which the data packet gets put in, and there is information given to it about where this data packet needs to go and what kernel needs to be launched. So, all that this tool does is it picks out the packet from the queue, moves it to the data, and launches the kernel. And it does that. It takes care of the complexity here lies in that it takes care of scheduling the moves and transfers so that the latency is hidden. It doesn't try to do anything more complex than that. Like I said, the most complex part of most of these tools tends to be the inferencing, and the tool doesn't do it. It just provides the provides the way of making things happen that you want, that you, the user, would be telling it to happen. For the mechanism of mapping work to computational targets, we have written a very limited domain specific language, or rather we are using a very that expresses the recipe of time stepping. So, it says that I want this sequence of physics operators to be invoked in this order, and I want this operator to be computed on this device. These are the dependencies. These are the operators that can operate in parallel. These have hard dependencies, which means that you need to sequentialize them. And the translator, then the code generator, just converts it all into Fortran code for us. But again, it is, you can as easily, the code generator is the easier part of it. So, you can as easily have the code be generated in C or C++ or any other language that you choose to have, right. So, and all of these mechanisms then make use of the composability that we already had in the code, and the tool set, it's the composability of the tool along with each of these tool sets that then provides completely independent tool sets. So the runtime orchestration system doesn't need to know anything about the macroprocessor, doesn't need to know anything about the code generator for recipes. They work independently, but it is up to the user, the person who wants to run the computation, to decide how to stitch them together so that you have an application. In the end, so what happens is that all of this black box is where the magic of making code performance portable on heterogeneous platform happens. In the end, you get a fully assembled and configured source code that can be fed to compilers like any other source code that you might have written, from the simplest to the most complex, and that generates the executable that you run. What that means is that at this stage, this is not assembly language or any intermediate representation or any of those more complex things. This is the code written in your own source code language of choice, high level source code language of choice, which means that you can inspect and modify it at this level. And actually, you can inspect and modify it at any level. So, design philosophy is to constrain the semantics so that simple tools can accomplish the needed transformations, that the individual tool should be maintainable by non-experts. So the inferencing here is done by human in the loop, right? Traditionally in high performance computing, there have always been people who have prided themselves on being the ninja programmers who could write a code that would maximize the performance on the target platform. That has become increasingly harder because it just isn't possible anymore to program, as they say, program to metal, because there is lots of code to write. So what our tool chain is effectively doing is, if you as the human in the loop know what you want done with your code, this tool chain is just making your job easier. It's letting you still orchestrate your the calculation in the way you want, but it's just making the job easier by providing you with ways in which you can express the work that you want done on the code, the transformations that you want done on the code at a much higher level than you would if you were actually coding directly to the hardware. So for the physics code, there are the macros, then there is the directives that have optimization hints. For example, you may want on a CPU, if you have pulled in a row of stencils, say, you would want to apply all of the operations that need to be applied on that stencil all at once in order to maximize spatial locality of data and therefore cache utilization. Whereas when you're operating on a GPU, that's not the best option. You want to send as many rows as possible simultaneously so that you've given enough you've generated enough work for the GPU, and so there are those optimization hints. What we also allow for is platform specific information to be stored, in the sense that on this platform, these are the devices, and therefore the work can be distributed among these devices, and these are encoded in form of templates, not C++ templates, just templates that have say certain time stepping options that are suitable for that particular platform. There is a library of runtime configurations, the pipelines that you can build for making the runtime tool execute appropriately. And so the tools then come in here. The optimizer and the macroprocessor generates the code for the target device. The human in the loop decides which templates and runtime configurations to use, and that puts together a recipe for control flow in time stepping. And then in the next stage, the translators generate source code for physics operators, source code for time stepping and runtime pipeline, and then finally the code assemblers puts it all together, and the fully assembled configured code is now available. In any of these stages in between, it is possible for the human in the loop to inspect the code and modify the code. The performance portability now in an ideal situation is going to be as simple as a new platform comes along. someone has to do the hard work of figuring out what are good templates and good runtime configurations for that platform. But once you put them in the platform specific information, if you didn't want any other change to your code, you're good to go. So, what this is basically separation of concerns taken to its logical extreme, in that it exists not only in the code, but it also exists in the tool. And the reason why I've explained it in this such a detail is so that the mental model that you have now of design is, I need to do this kind of design for this kind of work that my code needs to do, this kind of design for this kind of work that my code needs to do, and where is it possible to do separation of concerns, and things that you ought to be thinking along the lines of as you are writing your code. There are certain other rules of thumb that you should keep in mind as you are designing code for extreme scale platforms. It is that, of course, you have to have hierarchical parallelism, but one thing that is going to be happening in any instance of execution is that your code is going to be running with thousands of threads. And so you absolutely have to think about thread safe code and basically an ability to handle many threads without breaking your code. So things like race conditions, etc., are much more likely to happen, and therefore the simpler you keep your logical flow, the better off you are going to be. You have to design for a hierarchical memory space. You cannot make assumptions about the data locality that you will get from different kinds of memory, and therefore that you need to keep in your abstraction design. And another thing that is going to be very challenging now that we have many different flavors of memory, many different flavors of devices, that if you're doing any allocation as you're writing your code, keeping track of the memory allocation and deallocation is going to become that much more complex. Because you, in writing code, you always do this trade-off between how often you want to allocate and deallocate, and because that has its own associated cost. And therefore, keeping track of the memory that you're using and that you need to deallocate and reuse, et cetera, is going to be complicated. So you have to think about design patterns that count, keep track of, and reuse memory as much as possible. The last one is reiterates the point that I made earlier, is that as much as possible, keep your code general and not bind it to a specific option, a specific model, a vendor supplied way of doing coding until the very end. So complete your design and then add in vendor specific or program model specific options into your code. So the takeaways from this design module that I want you to have is that performance to the key to both performance and longevity of your code is in careful software design. That extensible should absolutely be built into your design, because you never know how your code is going to be used. In fact, you yourself may want to use the code in a completely different mode a few months down the line. You should make your design independent of any specific programming model, and it is the composability and flexibility in your code design that helps ultimately with performance portability. And with that, I can take all of any questions that people may want to. Is there a break after this, David? Yeah. Okay. So yes, I can take the questions now, and we can also continue the discussion if you have during the break. So, question?
So for the template macro Python library, is that a separate project that other people would be able to use, or is that just something that's customized, integrated into Python?
No, actually, this is a tool that anyone can use. The thing that people will the template translator is completely independent, right? So that one you can just pick up and go today and just do it, because it's written in Python, it takes in the macro definitions are put in .ini files, so the standard Python. The thing that we have added is the inheritance mechanism. And so it's this inheritance mechanism that you might need to customize for your own code. But other than that, it's just usable. And the inheritance mechanism basically is about arbitration on which definition to use where, if you have multiple alternative definitions. I think we are still just calling it macroprocessor. Yes?
How portable is the module that we, as a Flash user, I have created modules new to that not in the Flash, but if I want to use that, say AMRX in the Flash X, how portable is it? Can I just copy the folder and just put?
So AMRX is supported, which means that you should just be able to use it. Okay. But supposing you, but what you cannot use without some modification is these tools that we have built. And the things that you will need to do for these tools is, for example, the refactoring with inserted macros is left to the user, to the developer, right? So it's your job to think about where you want to insert those macros. The physics unit itself, that's just pretty much all it needs. The one more thing that it may need to do is to express how you want the data packets to be generated for your physics unit. I think those are the only two things that you need to do.
I'm concerned about the way, so I work on particle. So the way particle is handled in Flash, the parameters, and the way the AMRX handles the particles or distributes it is slightly different, I guess.
It will become similar in very near future. Because what AMRX realized was that their native octree mode is not as performant as Paramesh is. And so we have built a library called bittree, which is a bitmap. They are incorporating that into AMRX. Once bittree is incorporated into AMRX, Flash's X's particles unit will work seamlessly with AMRX2. Other questions? Yes?
So in the situation where you have a commercial package that you start off with,
Yes.
and you start developing tools to work with it, but your research moves away and their per package doesn't develop, how do you make the determination to basically break off and do your own thing and abandon trying to fit a square hole into a round, or a square peg into a round hole? Does that make sense?
It is actually a very non-trivial question to answer, right? Because it depends on how much work you're willing to put in, because this is much more of a refactoring question. If you have access to the source code, then your approach is going to be completely different from if you don't have access to the source code, right? If you have access to the source code, then you take a look at the code, and as you refactor it following these principles, which means that you may not need to recode your math all over again. You may just need to structure the code. Actually, that's how Flash evolved. It started out as an amalgamation of 3 different packages, and then slowly structure was imposed on it. If you don't have access to the source code, then I don't see any choice other than start writing your own code in whichever way you want to proceed.
Okay.
Right?
And then when you start writing code, there's been some talk about people writing code such that you can't tell who was a contributor to a particular section. In other words, imposing some sort of a style guide so that it becomes uniform. Is that a good idea to, as far as you give up freedom and flexibility for creative thinking, but you then get readability and uniformity? What's the trade-off between those two?
So you have to have coding standards. If there are multiple contributors to a code, you have to have coding standards. And you have to have other practices in place, such as how much documentation to put where. Then policies for what kind of tests you're going to be contributing, et cetera, because you want, so the flexibility lies in designing your algorithms, designing your data. Actually, even in data structures, you may not give complete flexibility, because if everyone can go and build their own data structures, then your performance can be shot if they're contradictory to one another, and you just end up doing many, many transpositions. So that is why when I said that there were two different life cycles that you needed to follow for infrastructure and physics, it is that your infrastructure in some sense dictates the standards of the code, because it might want to own the data structures that others have to conform to for it to be useful code and performant code. Sure. We can take a break, or if there are one or two more questions, I can take them. Yeah?
Thanks for the talk. I'm wondering about which best practices are highest priority, because there could be a list of 200 best practices maybe, and it's easy to say, oh, you should do all of them. But like, for example, to me, using Git and source control is probably the number one thing that I would recommend. And it doesn't matter if you have a README about how to contribute if you're not using Git at all or any kind of source control. So is there like maybe a resource with kind of starting with the very first things, like a sorted list maybe of best practices?
Wasn't that in David's talk?
That was in David's talk, the pointers, and the resources from their top point to the best practices. But I would argue that if you're operating in extreme scale computing, you really cannot afford to ignore any of the topics, actually most of the topics that we are talking about today.
But given that most projects ignore most of them, you want to start somewhere. You can't just drop the hammer on a project. You kind of, what's the next incremental improvement? And yeah, there was the best things to do with the good enough things to do. But
and the PSIP process where you do it one by one. And so only you can be a judge of what is the highest priority for you.
okay.
So some part of the social aspect, you want to know what your team is willing to accept as the next step. You can go to a list and see that maybe testing is the next thing, but if they're completely doubtful about that, no one ends up, what would be the point of spending energy in there?
Yeah, I've never seen a sorted list of roughly. Yeah, I can kind of ballpark it. I'm really like this. This whole day is my jam, so I could make something up, but I've never seen like resources like that.
Yeah, can I add? I don't know. So I think one of the points is that what is going to be most valuable for your team depends on your team and your situation at any given point in time. So your sorted list might be different than his sorted list or her sorted list, right? And so I think it's really about thinking about what is, I mean, you can look at these things, any of the common lists, and say, what is going on in my team that's giving us the most pain in our software development processes right now? And pick that one as your next priority to address. That's what I'd really encourage. So, for example, if you're not accepting outside contributions, or you're just a little team and you don't really care if other people contribute, then all this stuff around documentation for contributors may not be a big priority. But if the code keeps changing out from under you and it's not working right all the time, then maybe implementing testing structures would be a high priority.
I would say actually, irrespective of what people are doing, testing ought to be the first priority for anyone and everyone, because how do you even have faith in the results you're producing if you're not testing your code? So that's my personal opinion, but yes, to me testing is the single most important thing that every code project should incorporate.